Hello everyone. Let me first introduce myself. For those of you who don't know me, my name is Hector, and I teach here at the School of Creative Media. I'll be the speaker for today. Tomorrow the same talk will be conducted in Cantonese, but don't be scared, it's not by me. It will be done by my collaborator Sam Chan, who is here today. So if you wish to come back and hear it in Cantonese and notice any differences, you're very welcome to attend tomorrow or let anybody know. The first thing I have to tell you is that I am not feeling well today. If you walk outside and look at the weather, you probably can imagine the cause. So I apologize if my energy is a little bit low and my voice does not project well. Can you hear me in the back? Okay. So please forgive me. If you can't hear something that I say, just raise your hand, throw me a shoe, or just express somehow your inability, your discontent. So anyway, welcome. This talk is part of a series of events leading to and around an exhibition on algorithmic art that will begin in City Hall on December 27th. And I am one of the artists who will participate. There will be a number of other artists. So this is part of a kind of series of educational events that are being organized around that exhibition. We have a program at the entrance, and you're welcome also to look at the website for any updates. The talk today, I also want to say, is going to be a quite introductory talk. So I hope that it's not too introductory for some of you. If it is, just scream. This is Hector, 5D, I'm a guy, and I will do my best to speak more quickly and do 5D, as much as I can. It's intended for a general audience as an introduction to some techniques that we use to analyze movies and to make art using the movie heritage. We're going to start with some very, very basic material and very quickly move on to machine learning and fluid dynamics. So it's going to be a bit of a steep curve today. All right. Anyway, welcome. Okay, so this is me, Hector Rodriguez, and the basic theme for today is we're going to repeat a keyword that is very important to this talk, and to this whole series, which is STEAM. I think probably a lot of you have heard of this idea of STEAM education: science, technology, engineering, mathematics, and the A stands for art. Some people call it art and humanities, some people say art and design. So it's an idea that was proposed by the Rhode Island School of Design in the US, and it became part of their curriculum. And it's something that we are holding here in the School of Creative Media. It's the idea of integrating art, technology, and science and math. So a lot of the work that I do as an artist, and which I will show during this talk, involves using mathematics to analyze films. Okay. So I have about 150 slides and many video clips. So did you bring a foldable bed, or I'll try to move on. Okay, let's start with something very, very simple, kind of stupid, and forgive me, but I wanted to go step by step, right? We start with the idea of an image. And I'm going to assume today that all the images that we deal with are grayscale, okay? You might say, well, what about color? There's a lot to deal with just to talk about grayscale images. So images today we will talk about are grayscale. Sometimes we will be analyzing color films and color images, but we will always convert them to grayscale, meaning black and white. And we will assume that every image is an array of pixels, a two-dimensional array, and that every pixel can be represented by a number. The range is a little bit arbitrary, not exactly arbitrary, there are reasons, but we will assume that the numbers, as in this example, right, these are real numbers from this region here, from a movie, I don't know whether you like European art films. This is Alphaville by Jean-Luc Godard, and these are the real values as a range between 0 and 1. 0 being black, 1 being white. Other images can be represented as from 0 to 255. 0 being black, 255 being white. So since pixels are represented by numbers, then we can treat pixels and images as mathematical objects. So we can perform operations on them. One operation is we can multiply a whole image by a number. Another operation is we can add images. All we do is we add the numbers. So here's an example of an image multiplied by a number. And basically what we do is we multiply every pixel by that number. And this is the result. Multiplying by 0.4 will make the image darker. This is more complicated, where we take an image, we multiply by a number, we take a second image, just a white image, multiply by a number, and then we add the result together. Okay? When we say that images are vectors, we mean that we can perform these operations. We can multiply images by numbers, we can add images together. When we think about an image from a mathematical point of view, a very basic idea is that an image is a function. You all know what a function is from math, right? You can say it's an input-output system. Let's say a function like x squared can receive many inputs. Let's say the input is 3, the output would be 9. Okay? So in this case there's only one input and then one output. We can think of an image as a function that receives two inputs, the x and the y, and then as an output tells you how bright is that pixel in the x and y location. Okay? So this is a very important starting point to think about images. Images are functions. And we could draw that function where here a 3D version where one axis is the x location, one axis is the y location, and then the perpendicular axis to these two represents the brightness or intensity of the pixels. Okay? So here is an image from a film by Andy Warhol, and every pixel is represented by the height. So this is like a graph of the function, you can say. Here's another view. I don't know why I give you another view, but here is a 2D version, so that you can see more clearly. We just take one row from the image, and we represent the changing intensities of pixels as a curve. So this is just that row by the forehead of this map. So you can see, for example, this point where there's a very steep change in the curve probably represents the change around here in his forehead, right? Where it goes from very bright to very dark. Just to help you visualize it better, here is the same curve, but with the actual value of the pixel. So you can see clearly, here is maybe where you have the dark hair, and this is the wall. You can see, and this is something very simple but very important, that in some parts of the image, the brightness does not change very much. In other parts, there are steep changes. And it goes up or it goes down. So this is crucial because one of the basic concepts that we use when we are manipulating images is the concept of gradients. So when we talk about the gradient, we always talk about something that happens at a pixel. So a gradient as a pixel just tells you how the brightness of the image is changing around that pixel. Okay? For example, here just considering the horizontal element, we can say that around here the gradient is very steep, right? So around these pixels it's changing a lot. Around here there's not so much change. We can visualize the gradient by drawing a line that is tangent to this curve at that point. So in some parts the line would be almost horizontal. In some parts the tangent line would be much steeper, and that tells you there's stronger gradient. When the image changes from dark to bright or bright to dark, there is a strong gradient. Now this again is very simple, but it's something that's really important in a lot of applications to analyze images. For example, here we take a pixel from the Andy Warhol film, not a pixel but a whole area, and we see that in all of this area, in all of these pixels, there's very little change. So if you pick any pixel at random, you see that all the pixels around that pixel are pretty much the same. So there's no gradient. For some reasons, this is really important when we try to track motion in films. We will see why later. Here is an image with gradient, but in only one direction. Let's say that you look, you begin here, you move up, you can see that pixels are changing, right, as you go up. But if you pick any row and you move along, there's no change. So there's no pixel along the horizontal direction, but sorry, no pixel. There's no gradient, but there's gradient as we move up. So here we have gradient in one direction. Here's an example. Here there's gradient along both directions, but still it's mainly gradient along this direction. And here's an area with gradients along both directions, the nose. Here around the nose. This will be important later on when we talk about motion tracking, because when we try to analyze the movement of films, we often want to track areas that have good gradients in both directions. It might seem like a simple thing, but it's very important in a lot of the work that we do. Okay? Okay so far? How do we compute gradients? We often compute them using an operation in math called a convolution. And this is an idea that's not only applicable to pixels, but it's applied in a lot of image processing. If you ever study machine learning or AI, you will hear something about convolutional neural networks, which is an expression that people use to scare you, and it is scary in a way. And we use this operation called convolution. What does convolution mean? It's a simple but very powerful idea. The idea is you have an image which is an array of pixels. Here the pixels are a different range, so they're not between 0 and 1. But imagine this is the image, input image. Then we apply, let's say, a filter, or we call it convolution kernel, which is another matrix. It can be 3 by 3, 5 by 5, 7 by 7, normally odd number. So we don't have one that is 4 by 4 or 6 by 6. With a set of numbers. What do they do? Let me explain. The objective is this. You take an input image and you produce a different image which somehow gives you some information about the input image. The kernel is used to transform the input image into the output. How? Let's say, and we're going to do this to every pixel. But let's say that we take this pixel here, which I don't know if you can see in the back, it's a 6. Okay? And what we're going to do is this. If the pixel is 3 by 3, we are going to look at all the pixels in the 3 by 3 window centered on the pixel that we want to replace or we want to process. And we do this. We take the first number, the one in the top left, in the kernel, and we multiply by the number on the top left of that window. We take the second number, which is a 0, and we multiply by this, which is a 0. Third number, which is a 1, we multiply by that, which is a 1. And so on. And we do 0 times the 1 in the center. So we do these multiplications. And then we add all the results, and the results will give us the value of the new pixel, which is -3. Is this clear? Now, this kind of pixel is, this kind of kernel is a very special kernel that we often use in image processing. It's called SOBO. So this is the X kernel. What does it do? It looks at this image, and if this pixel is a pixel with very high gradient, it will produce a number with a high absolute value here. Okay? So this will magnify pixels where around them, here and here, and this is a horizontal one. So this is just looking at change horizontal. Looking at the pixels to the left and to the right, there's a lot of gradient change. There's a lot of change in brightness, I should say. Okay? In this case, the number is 3 with a negative sign. The negative sign just tells you the change. If it's from bright to dark, it will have a negative sign. If it's from dark to bright, it will have a positive sign. So the sign, minus or plus, tells you the direction of brightness change. The magnitude of the number tells you how much. Okay? So what this set of numbers will do is it will highlight those pixels with a lot of gradient. So here are actually two kernels. This one is the same as in the previous slide. It highlights areas of horizontal gradient. This one, GY, highlights vertical gradient. So this is one of the typical images that we use for demonstrating these things. Einstein. To say that this is Einstein reminds me of once I saw a Chinese movie which showed you the Eiffel Tower and they said underneath Paris. So these are, you can see those areas in the image with strong vertical, horizontal gradient. These are strong vertical gradients. So these are called the Sobel kernels. Altogether we call them the Sobel operator. You will, if you ever do, say if you work in processing and you use OpenCV or other libraries, you will encounter these kernels and this convolution operation. So this is one that highlights more change around the X, this more around the Y. Again, just to show it again, this is an original image, and this is the result of convolving. Remember, convolution is applying these kernels. Okay, so here we convolve the image with only one, the vertical gradient. So you can see there's a lot of vertical gradient here. And this shows you only positive gradient, going from dark to bright. This one shows areas with both positive and negative gradients. Okay. So here, basically, these numbers will have a negative sign. So just for rendering, we show them positive. Here is, again, we are applying these two convolution kernels to an image from Alphaville by Goddard, and these are the points that have gradient in either direction, so I'm not separating them. Here I'm reversing the color scheme, showing the points as black and the background as white. It doesn't really matter, it's just a convention. Gradients have a direction. I don't know whether you can see it clearly in the back, but the arrow tells you whether it's the direction of going from bright to dark. So here are arrows telling you the direction of the change. Here's another. Now, I developed a project called the Entropic Envelope, which used this idea of gradients to analyze the rhythm or the flow of images. I should tell you something. People think I am an artist, but before I was an artist, I was a film scholar, and I have a PhD in cinema studies. But I always felt very dissatisfied with a lot of ideas in cinema studies, because there are many beautiful things about cinema for which we don't have words. And one idea is, we know that cinema is like a flow, like a melody of images, but we don't know how to describe it. And I thought I would try to develop a mathematical technique to describe the flow of images. So I use gradients to represent how a movie is changing over time. The procedure is quite technical. I have the math in a slide, but I will skip it because I'm in a kind mood today, maybe because I am sick. But what the procedure does is simple. It will take an image and divide it into 4 areas, just 4, like 4 quadrants. And it will look at the gradients in these 4 areas. Then it will look at the next image, and it will try to compute how similar or different are the gradients in the next frame compared to those of the previous few frames. The computation is more complicated than this, because at that time I was reading something about philosophy, and there's a philosopher called Edwin Husserl who wrote a lot about time consciousness. So I tried to express some of his ideas in the software, but I will not talk about this today. Still, you can see that when the curve goes up, that tells you that the gradients are changing a lot from one frame to the next frame. Then later on, when they stabilize, the curve goes down. So here, for example, you see the main character is walking, and at one point there is a column, right, a pillar, which enters the frame. And that creates a kind of a big change in all the gradients. So the curve goes up to signal this. Later on, when the image becomes more stable, you see just the guy walking and it's pretty stable, the gradient goes down. Here's an explanation with some I should tell you, although I did not have this, I had not opened this, but let me do Entropic. This project is called the Entropic Envelope. If you look it up online, it's been published, but I also have the essay in my website. It's called Concept Script, and there is a simple explanation, and then for those of you who love math, ta-da! Okay, never mind. So here is the math. Actually, the math is very simple, secondary school level, really. But you know, once one of my students said, "Oh, Hector, you're amazing! You created your own formula." And I wanted to tell him, look, it's not E equals mc squared. It's really quite simple. But you have the whole mathematical explanation, if you like. I'm sure you will rush to read it after this talk. No, maybe not. Okay. So here are some other examples. Obviously, when there is a cut, the curve goes up, right? Again. But it's not only when there's a cut. A lot of times... Oh, here's another cut. Sorry. Here, the main character lights a cigarette and then turns off the light, so you can see that the gradients change. So you can see that when the gradients change, this curve goes up. Again, here there's no cut, but the camera is moving as the car is moving and the background is changing along. Here is very bright and detailed. Here there's less detail, so there's change in the gradients. Some other curves. And here's a different film. It's a film made by an experimental filmmaker called Stan Brakhage. And this is a very strange, radical film where it's meaningless to even talk about cuts or camera movements. He made it without a camera, using an optical printer, by using leaves and wings of animals. So it's changing very radically. So you can see the curve going nuts. I show you, I think some of you have seen these videos, so forgive me, but I show this to you quickly and move on to other new things. This is the film called Alphaville. So, could we turn off the lights maybe in the back, if you don't mind, please? Okay, never mind. The red line represents the current frame. So, this is the curve, and this is what happens in the current frame. You can see suddenly the door is coming, so the curve goes up a lot. And now there's a cut, but now it's very stable. But whoop, whoop. Sorry, I should not give you the sound effects. Now it becomes stable again. Now unstable. So this really tells you that you can say the visual music of the film. Now again stabilized. Here's a film by Alfred Hitchcock called Rope. And the film is in color, but never mind, because I turned it into black and white for my application. Again, here there's not much change. So the curve is down here is very stable. But now the camera begins to move, the curve begins to move up. We have different gradients in the image. Now it stabilizes a little bit, but not too much. And again, yeah, different gradients, right? All these horizontal and vertical lines. But now, okay, it's stable. And now there's going to be a cut, so this thing will jump up. I promise you there's a cut. Ah, there we go. And you can see the curve went crazy. Most of this movie by Hitchcock, there's not a lot of cutting and the movement is very slow. So the curve doesn't go up a lot. And finally, I show you Mothlight. I mean, this is a crazy thing to see. And you can see, so this curve helps us to understand different styles in movie making, just by looking at changes in the gradients. Okay. I'll show you just a little bit of this, although I think some of you saw it in my recent exhibition. But this represents the current frame, and this moves up a lot when there's a lot of changes in the gradients, and this represents the previous frames. It's a 3D version. You know, it is interesting, I often say this to people. I developed this project as an academic project to analyze films. And it happened that some people in France saw it, and I love people in France. They discover things that other people don't discover. So, they like Jerry Lewis. You don't know who Jerry Lewis is, never mind. Anyway, they wrote me and said, Hector, can we show this artwork of yours? And it was shown as a piece of art. So I'm really interested in the fact that, for me, a lot of science images are more beautiful and interesting as art than many of the images made by artists. I know this looks like a Joy Division album cover, but
Yes.
I didn't realize that because I'm a... All right. So here are some images. We can turn on the lights now. Okay. Now I said that images are functions. When we deal with time, an image is a function of three inputs, three variables, x, y, t, t representing the time. And then it gives you the brightness. So this means that we can talk about also temporal gradients. What does a temporal gradient mean? Suppose you take a pixel or an area of pixels and you compare the brightness of the pixels with those in the next frame. Okay? So then when you take that difference, that is a temporal gradient. How do you compute the difference? It's very simple. By subtracting the two frames. Okay? So those areas that are stronger will become more intense. Okay? This is called frame differencing. If you ever work with, say, using processing or some other programming language like open frameworks, and you find the keyword frame differencing, that just means temporal derivative or temporal gradient, how an image is changing over time. This is very important. We will come back to this image later. Okay. One more comment on convolution. Remember the word convolution? I just used it, right? Sorry for saying this. I'm used to teaching my students. Some of them are here today, so forgive me. But sometimes I mention a keyword that I just mentioned 5 minutes ago, and they go, what's that? What does that mean? So, sometimes, sorry for this. I have a habit of repeating myself. So I want to go back to the idea of convolution, because this idea is not only used to obtain gradients. Right? We've talked about convolution to detect horizontal and vertical spatial gradients. But we use convolution for other purposes. So let me repeat again what convolution does very quickly. Right? We have an input image, we have a kernel with an odd length, 3 by 3, 5 by 5, 7 by 7. And basically what it does is it takes all the pixels centered in one pixel and multiplies them and adds them together. Right? So it multiplies each one by a weight. These are the weights. And then it adds them together. And then it replaces the center pixel with the new value in the output frame. And it will do this to all the pixels in the frame. Okay? We often, by the way, ignore the pixels on the borders because there's nothing next to them. Or we do other things. Okay. Is this clear what convolution does? So convolution can be used, and by the way, here you see the operation, right? This is a stupid kernel. It just takes 4 and minus 4. So here it multiplies this number by 4. 4 times 0 is 0. This number by minus 4, it becomes minus 8. And all the other numbers by 0. So adding them together, since 4 times 0 is 0, minus 4 times 2 is minus 8, it becomes minus 8. Now, how do we use convolution? One way is blurring. When we blur an image, for example in Photoshop, what's going on there is that we apply a convolution. In this case, the most common or easiest kernel to understand is this one. They're all the same. How many elements in the kernel? 9. Each entry is 1 over 9. So what this kernel will do is it will look at every pixel and will look at all the 9 pixels in that window and average them. So blurring is basically averaging nearby pixels. Anyway, in this application. So here's the result of applying this to this image. It's called box blur. But box blur is not maybe the most elegant approach to blurring an image. A better one is called a Gaussian blur. Have you heard of Gauss? German guy, any Germans here? Yes. So have you all heard of a Gaussian distribution or Gaussian curve? It looks like a bell curve, we say. So a Gaussian filter is one that looks like a bell in 2 dimensions, meaning that it has a stronger weight in the center and the weights become smaller as we move outwards. This kernel is 5 by 5. We also multiply by a normalizing factor. This doesn't matter, but I have to tell you one thing about kernels. If you're so inspired by this talk, you decide to go home and do this yourself, it's very important that all the kernel, all the entries in the kernel should add up to 1. If not, the kernel will change the overall brightness of the image. So this factor will just make sure that all of these entries add up to 1. So when we apply this kernel to this image, it will blur the image as well. And what it will do again is create an averaging of all the pixels in a 5 by 5, in this case, window. But the kind of averaging is more smoother, you can say. So this is called a Gaussian blur convolution. And the idea of a Gaussian blur is very important. By the way, let me go back. Sometimes when we're analyzing movies, there's too much information in a frame, too much noise. So in order to track movement, let's say that we want to analyze movement in a film, which we will talk about later, sometimes it's helpful to blur the image. Sometimes not, but sometimes yes. So Gaussian blurs are often used. They help us to get rid of noise. One guy who used Gaussian filters is this guy, Dennis Gabor, who invented a set of filters. His filters were just 1D filters used to analyze sound, but now we use 2D versions of his filters. The filters involve 2 parts. The first part is blurring an image. The second part is detecting edges in an image. This is quite dark. Can we turn off the lights in the back? Sorry for this. Hello. Sorry, you just arrived and I darkened the room on purpose. So these are the filters. And the filters, like I said, they have 2 parts. One part is a blur, which is a Gaussian blur. The second part, you can see, it looks like bands, right? Think of them as, you know, a sine wave? Think of them as a sine wave in 2 dimensions. And the sine wave, the wave in 2 dimensions goes bright, then it goes up, and dark, then it goes down. So it's like a 2D wave. And these are filters in different directions. Some are vertical, as you can see. Some are, sorry, no, these are diagonal. These are horizontal. Okay. Somebody help. So definitely tomorrow you get the good version of this stuff. These are vertical. These are diagonal, these 2. And the ones on top are horizontal. Let's have a little bit of light so the people who just came can sit down. Just a little bit. Can we have a little bit of light?
Just a bit?
Just a bit.
No.
Yeah.
A little bit.
Hello. All right. There we go. So how can we use these filters? So these are very powerful filters because these filters respond to edges in an image, but they're more powerful than just gradients. They respond to edges that have different orientations and different scales. You can see that some are bigger, some are smaller, and these ones you can almost not see. So these are called Gabor. Let me go back. Gabor filters from this guy. He won the Nobel Prize for something else, but not for this. And I applied this to film analysis those of you who maybe you came to my exhibition, so this is applying different filters to a movie by Mizoguchi, Japanese film. The film is called The 47 Ronin, and it's a very nice film because it highlights Japanese architecture. And can you see that these filters are all responding to the diagonal edges in this direction? These are responding to the vertical edges. These to the horizontal, to the diagonal edges in the opposite direction, and these to the horizontal. I'll show you a little bit of the clip, just for those of you who missed it. It's a very slow film. I love slow films. Here we go. And you can see there is a vertical element moving in, and these filters all respond to the vertical element. But here it disappears, and here it's just nothing, because these filters are only responding to the horizontal element. The last column shows a summary. So this is the combination of all of these filters, or this filtered image. This is using all of them. So here we're using very thin filters to detect thinner edges. Here we're using greater, bigger filters. Okay. So these are called Gabor filters. Here again, different sizes of horizontal filters. And it's interesting because you can see that some filters are bigger, some are smaller, so they can respond more interestingly than just gradients. Let's say we have this original image, and we just apply the Sobel convolution, which are normal gradients. They will respond to these edges and to these edges here, because there's a big gradient here, a lot of gradient, going from black to white, from white to black. Same here. The Sobel, the normal gradient operator, will respond equally to both. It will highlight both. Gabor will tend to highlight more those that have the same scale or the same size as the filter. So you can see that we are using a big filter, vertical filter, and it's responding more to these larger edges because than to these here, which are thinner edges. So it's very sensitive to scale, and it can be used to analyze different parts within an image. Here is a horizontal. Like I said, you see that it's like a 2D wave of bars going brighter and darker together with a blur. When we apply this filter to this image, it's basically again a convolution, but it's a more complicated convolution because it's a more complicated filter. It highlights a number of areas like the mouth, the shoulders. The eyes a little bit, but less because they are different size. And if you see, all the lines in the forehead are almost lost. So this filter really picks up primarily the mouth in the whole image, is the strongest response. So we can use these Gabor filters, for example, to analyze images. Have you heard of this Chinese artist Liu Bolin? So he's a really cool artist, actually. So what he will do is he will paint himself to merge with the background. It's like a camouflage. Sometimes when students are looking for me, I feel like I want to do this as well. So you can see this is him camouflaging on the background. And this guy, Chris Mata, did a project trying to use this method using Gabor filters to analyze some of his images.
The SP Mini project is about Gabor filters and camouflage.
There is a...
Lou Bolin is an artist who paints himself into the background of his photographs in an attempt to camouflage himself.
Okay.
Image that I processed using Gabor filters.
So I'm going to skip this an explanation of Gabor filters, which is a little bit more technical. But basically he's going to try to use Gabor filters to detect the presence of a person, in this case the artist, against a background.
Filters. This image was selected because of its mostly regular background. The hope is that the Gabor filter will be able to pick out textures corresponding to Lou's body that aren't horizontal like the stripes in the background. I first processed the image with a rather large Gabor filter to determine the general location of vertical textures in the image. As you can see, the filtered image shows that there is an area containing vertical textures. The next step will be to combine more orientations so that we might find a more rigid outline of Lou's body. Combining 4 more orientations gives us a much better view of Lou's body, with the background stripes completely eliminated. The second image I processed using Gabor filters was much more challenging, as you can see. The background is no longer one texture of horizontal stripes, but instead much busier with different textures throughout. A first attempt was made to use the same orientations that were used for the first image, but the results were much poorer this time around. This is due to the fact that Lou's body is not the only part of this image with vertical textures. A new strategy was needed in order to find Lou, so I presumed that wherever he might be, it would be probable that he did not paint the textures on himself as well as the background. I proceeded to find the orientations for the different sections of the background. The hope is that when all of these orientations are combined, there will be an area corresponding to Lou's body that is not as bright as the rest because he was not able to copy the background textures exactly. The strategy worked, and a dark human shape is able to be seen among the otherwise light spots. However, this might not be the easiest way to tell if Lou is camouflaged in the image.
Anyway.
Thresholding was implemented.
So I was inspired by this approach and made a work using Gabor filters to pick up the rain. Now, I love rain in movies. Very often I like the rain more than the story. And there is a film, I think maybe many of you know it, called The Grandmaster by Wong Kar-wai. In the beginning there are some martial arts fighting in the rain. I like martial arts, but I like the rain more. So I use Gabor filters to extract the rain from that scene. You still see the people, but they are like a black absence. This is Tony Love, by the way. The sound, by the way, required some AI to develop, but you can ask me during the Q&A if you want to know how I did the sound. So these are Gabor filters, and they are very useful to extract. We can have a little bit of light to extract different edges. We chose very thin Gabor filters, which responded to those rain streaks of rain in the image. So it's called the uncertainty principle rain. By the way, I'm not going to explain this in detail, but the reason why I call this work uncertainty principle is because Gabor's filters were designed based on the same idea as the uncertainty principle in quantum mechanics. So there's that idea there. If you want to know more about this, you can ask me, and I will ask you to ask a physicist. I can try to explain it as I can. We can also use Gaussian filters to find key points in an image. Very often, when we have a frame, this is an image from a Chinese filmmaker that I really love. He's based in Taiwan, called King Hu Qingchuan. And I'm now working on his films. And I wanted to get key points in the image, important points in the image. So what we did was simple. We used a whole set of Gaussian filters. These are quite large. And we just applied them all. And we found, this is the result of applying them to this image. And we found points in the image that have a stronger response to the filter than the other points around. So for example, the area near the nose of this guy has a strong response, and then we selected an area based on the size of the filter. So these are quite large filters, and they gave us some interesting key points on the image. For example, this area near the edge of this. Here's another one using smaller filters. By the way, the filters are much smaller than this. I just enlarged them so you can see them. So they pick smaller key points within the image. Okay? So these are all points that have a strong response to the Gaussian filters. So having talked about gradients and optical flow, and Gaussian filters to detect the overall structure and the shape of an image, the next section I want to discuss motion. And we're now moving towards the work that I will be presenting at City Hall. So let's use the keyword optical flow. You know the word optical, right? It refers to anything we can see. Optical flow means the apparent motion in a scene. We say apparent because if you see a movie, right, someone, in this case there's someone playing the drums. The movement that you see is not the same as the real movement in front of the camera. If the person is very far away, the movement will be very small, right, on the image. If the person is closer, the movement will seem longer, higher in magnitude. So optical flow is the apparent motion, the motion that you see on the image. And we usually represent it using arrows. How do we compute optical flow? There are many methods. Some methods begin by selecting areas within an image. In this case, we just select areas on a kind of regularly spaced grid. Okay? And we can select areas on with a smaller regions, make them far apart, make them overlap. There are different methods. And then we take every region and we try to locate the same region in the next frame in the movie. So here's a region which corresponds to the ear of this person, and we want to find the same region in the next frame. And if we can do that successfully, we represent the result as an arrow from the position of that region in the first frame to the position of the region in the second frame. So this would be an arrow, we call it a two-dimensional flow vector, which goes from the origin to the destination. And the vector has two components, the x and the y components. This represents the apparent motion in the scene. Next, anyway, that was just a mathematical description. This is actually a table of how the algorithm works to do what I just told you. So I won't describe it. You can see, though, that interestingly, the algorithm, in order to track one region from one frame into the next, it's using gradients. So it will use gradients when trying to track it. Why will it use gradients? It will use it because, you know, if you have a frame like this, two frames, you want to find this region in the next frame. You don't want to look through the whole frame. You want to look in a clever way, right? So first the algorithm will try to find it in the same area, maybe about here. And if you can't find it, it will use the gradients in this image to try to improve its search. Okay? How it does it is very complicated. There's a lot of math. Especially there's calculus and linear algebra. By the way, any high school teachers here, secondary school teachers? The reason I ask is, many people ask me, what do I think is the mathematical content that is most interesting for artists to learn? So if you're teaching secondary school and your students are artists, and you want to teach them some math that is useful for artists, I always say two things: calculus and linear algebra. Probability doesn't hurt. Other things, set theory. Anyway, so we use a lot of calculus and linear algebra in order to find a match. So this is a complicated algorithm, complicated process. But this was the first. I have to tell you this personally because some of you may feel like, Hector, all this math. We are artists. So I am an artist too. And it was this algorithm that got me started into math. A friend of mine said, Hector, you need to learn how to do this, how to program this. So once during a holiday I went to London, and you can imagine, what would you do in London during a holiday? Go to the theater? Party? No. I went to the hotel to program. And I spent the whole holiday programming this algorithm in that hotel. So this was the beginning for me of algorithmic art. And the result, of course, is that we associate with a frame, with every pixel in the frame, or with every region in the frame, an arrow that represents the movement. By the way, very often, before we can do this, we have to blur the image because it's too noisy. By blurring it, we lose information. And here's something really interesting if you ever do this kind of work. There is a major obstacle. Let's look at these two frames. These are frames from a film made in the year 1916, 16, called Judex, French film. Any French person here? They're good because they always correct my pronunciation. So it's directed by a man called Louis Feuillade. Something like that. It's a very remarkable film. So these are two frames. And if you can look carefully, there's some change in the frames. There's some movement. Take a look at this character, and if you look at her nose, you can see here she's moved forward a bit. Can you see? Yeah, okay. Look at this vertical line. Oh, move. Yeah, so it's behind her now. Also, this character is moving back. Look at this vertical line here. And here, you can see that she's moved back a little bit. Let's say we want to track movement in these two scenes. And let's say we want to track every area. There's some areas here that are very difficult to track. Look at this. Imagine that we have a region here, let's say it's a rectangle or a square, and we want to track this region from here to here. This frame. How would we know where it moved? It's all black, right? There's no gradient. So very often we don't want to track areas in one image that have very low gradient, spatial gradient. So gradients are again very important. Our eye responds to gradients. Without gradients, there will be no sense of movement. In fact, if we ask the computer to just look at this area and track it, the computer may produce some result that is nonsense. It might think it went up here. It is very. Imagine yourself. Imagine I just show you this area, and then I show you maybe a bigger area in this frame, and I ask you, where did it go? Right? So one thing that we can do, faced with images with a lot of areas with no gradient, is we can detect what we call corners, which are areas with high gradient. I showed you a little bit of that before from another and we just track those areas. Why is this so horrible? Okay, hang on. Sorry for that. So here are some marked green, some areas with a lot of gradient, which were detected by an algorithm called Harris corner detector. Notice that there's no corners here. Something else that we can do to clean up the image is we first track the image, and we track regions all over. We don't care whether there's gradient or not, and the result will sometimes be nonsensical. For example, up here, this is the result. It's complete nonsense. Look at this arrow here. This is all a big mess. Look at these arrows in red. And try to find those arrows that seem to be nonsensical because they are very different from the arrows next to them. And we replace them and try to interpolate arrows in between. So you can see how we have cleaned this up. Now it's much cleaner. We just found those arrows that look very different from the arrows next to them, remove them, and use some math to interpolate in between. By the way, this is part of the work that we are doing for the new exhibition. Okay, here again, this is a very difficult shot to track. It's a low, the camera is on a low angle, it's down here looking up, and there's a woman playing the drum, so she's moving her hand to the camera, sunlight on top. The result is, you can see in some parts, really messy. So we identify those messy arrows, and we replace them using an interpolation method invented by Laplace. Okay, so talking about optical flow, let me describe a little bit how I used optical flow in one of my recent projects, which is called Gestus. So if you saw this work, let me show you maybe a little bit of a clip first, and then I will explain. This is the first time I explain in public how I made this piece. So before I play it, let me tell you a little bit what's going on. So this is the film that I mentioned before called Judex, and I played the whole film in the center. Actually, not the whole film. We haven't had time to render the whole film, but the final version will include the whole film. And then the software will analyze the optical flow, the apparent movement in this scene, and find 8 clips from the same film that have a similar movement. The software doesn't care whether the movement is a man, a woman, a dog, a car, a tree, whatever it is. It will just match movements that have the same direction and speed. So you can see he's moving up. Now he's moving up. So he's matching a man with a horse before. And there with a car. Oops, gone. There, here with a car. So it doesn't, there's no object recognition. It doesn't care what the object is. It only looks at the movement. You will see a dog, I think, soon. Huh? Oh, already. Did you see the dog? Yeah. Let's see the dog. I like the dog, so let's just... Where is the dog? Before this. Ah, there we go. Let's go again. Sorry, we have to see the dog. Look at the hand. Look here. The dog. Did you see the dog moving up the same as the hand? I should slow this down, I think, even more. Okay, we can turn on the light. Thank you, Winsome. Oh, is it you? No, whoever. Never mind. Someone. Thank you. Maybe. By the way, it's really interesting. If I don't tell people what this is about, they come in, look at the work, and they don't know that it's about matching movement. most people don't understand that it's about matching movement. But during the exhibition, there was a group of students who came to see the show. Actually, my research assistant Sam Chan told me about that. There was a group of students who came to see the show, and some of them were older, some were younger. These were primary and secondary school students. And one of them was a very young female student. She, like I said, most grown-up people don't understand that this work is about matching movements. But this girl came in, they all sat down on the floor to look at the work during the exhibition, and the girl said, "Look, they're all moving in the same way." And her teacher, who was there, said, "I would not have noticed." And I think Sam's observation is that maybe children love movement. They love cartoons, and they are more responsive to movement than grown-up people. I always feel like, what happens to us when we grow up? We actually see less, in a way. Okay. So, how do we make this work? I think I'm running late, so I will 5E. And if you want me to slow down, just say, "Hector, man." But I've never explained this to people. How do I make this work? How does it work? First step is, for every pair of frames, we compute the temporal gradient. So we have 2 frames, we subtract, and we obtain the difference. Why do we do that first? Because we don't want to track areas that don't change. We know there's no change there. So we're only going to track areas that we know have changed. Once we have this difference, which is the temporal gradient, then we find corners, areas with good gradients to track. Again, only in those areas that we know have changed. We know this guy has not moved much, so we don't track this guy. We just find corners and we compute the optical flow. Then we create a grid, and we basically average all the arrows inside each cell. So here there may be many arrows. We just get the average arrow. Then we find, if you look carefully, you find many of these arrows are connected together. So we find connected regions. Here there are 3. The head of the woman, the body of this woman, and the head of the other woman who is moving back. So we find 3 regions, and we summarize the movement in each region, and again we take the average. Okay. So here's the original arrows, then we quantize them with a grid, then we summarize like this. Then, now we can, if you want, compare different vectors. So for example, if we have one vector in one frame, which might be going in this direction, and another vector in this direction, we can create a diagram like this and count how many steps. So from this arrow we will go 1, 2, 3. So the distance, the difference between them is 3. Okay. So we use this method to compare vectors. And using this measure, we compare vectors in different frames. More details I can give you if you're interested in the Q&A. I use a method to do it called the Hausdorff distance. Basically, this is how we compare vectors. And then we render images with similar movements side by side. Okay? Okay. So we're now coming to the work that I'm going to present, and completely new stuff, but bit by bit. Optical flow is interesting because when we think about camera movements, different camera movements have different kinds of optical flow. So here's an example of a movement which is just a pan, like this. All the optical flow would move like this. This is a tilt. The camera is moving like this. So you can see from the optical flow. And this is a zoom, where all vectors are moving outwards. Here's an example from the films of King Hu. Here's a zoom where the camera is zooming in. Here's a woman playing the drum. The camera is zooming onto the drum, and most of the arrows are moving in this direction. Because as the camera zooms in, everything seems to move in this direction. We're going to use this method to analyze movement in King Hu's work. Okay, but we're now going to take a little bit of a break. No, not a real break. Don't go to the toilet. But a break from talking about optical flow, because we have to introduce another idea, and then we will come up to the real work. So the idea is one which is again based on another work that some of you might have seen, called Approximation Theory. This is based on a work I did with a mathematician called Felipe Cooper. I will be very quick, because I only have about 10 or 15 minutes. So I'm going to skip. But I don't know, how many of you came to my exhibition? Can you raise your hands? Okay, not so many, okay. And someone in the background. Yeah, I know you were there. Thank you. Okay, but very quick, because this idea is very important in terms of the work that I'm doing now. The idea I want to talk about now is ignore movement, forget about movement. Let's go back to talking about pixels. We will come back to movement in a second. The idea is the idea of a dictionary. What do I mean by a dictionary? I don't mean a dictionary of English words or Chinese characters. I mean a dictionary of images. Imagine that I give you one image. Can you recognize? Is a runner? Actually, does anybody recognize this guy?
Jesse Owens.
Jesse Owens. So we have an image from the Berlin Olympics, which I think is an interesting period. Berlin Olympics of 1936, I believe it was 36, of Jesse Owens. And imagine I give you this image. Okay? Then I give you, in addition, a whole set of very simple images. Every image is like this. It's a rectangle, and there's just one line in that image. Okay? The line divides the image into two parts. One will be black, one will be white. Okay? And I give you many images like that. 10, 20, 30, 40, 50, 1,000. And I say to you, you have a machine here. In the machine, there are some sliders you can control. By moving one slider up or down, you make one of these images brighter or darker. Remember in the beginning I said you can multiply an image by a number times 0.4, 0.5. So you can multiply the image by a number moving the slider. And you have all these images. And I say to you, by moving the sliders up and down, try to change each image so when they get mixed together, they look like Jesse Owens. So you have an image here. You have then many images and a controller. I don't know what is going on, but never mind. And you try to reproduce, or in math we say approximate, the source image by combining all of these images. Is this okay, clear? Okay? So here we are just using 30 images. The computer can do what I just asked you to do, to move the sliders up and down. So some images become brighter, some darker, then we combine together to try to reconstruct Jesse Owens. The computer can do this automatically. It will find the best way to combine all the images to produce the result. So this is the best reconstruction of Jesse Owens with 30 images. Okay, here we're using 60, 120. You know, I like this one, right? This is 360. Is it beginning to look like Jesse Owens? It's in between. I like these images which are in between abstract and representation. Here's closer, and here you can really see, and one person even recognizes that it's Jesse Owens. So here we're using a 1,920 images. This whole idea has a lot to do with data compression. Dramatic science. Okay, let me explain why. Imagine that I say to you, I'm going to give you many images. Here you have this dictionary of simple images, okay? The computer will always find the same method to combine them together, right? How will the computer do it? It will multiply each image by a number. Let's say I have 100 images, or 120, okay? The computer will say multiply the first by 0.2, the next by 0.1, the next by 0.005. Instead of storing the original image, you can just store these numbers. If we always use the same dictionary, then each number tells you the contribution of each element. So let's say your image is 10 by 10 pixels, that's 100 numbers. But imagine your image is 500 by 500 pixels, huge, right? Then we can compress the image, of course with losing information, by giving us just 100 numbers. The first number is the weight of the first image, the next number the weight of the second, the weight of the third, and so on. So in a way, by finding a dictionary, we can compress an image. And we are free to use different kinds of dictionaries. This is the result. Yes, just see all this. The more images we use in our dictionary, the better the reconstruction. For example, here I'm using only 10 elements in the dictionary. So I'm using a set of images. I'm not here using lines. I'm using images from another film. So I'm using a different approach. Never mind. And here's the frame I want to reconstruct. So I'm trying to reconstruct this with only 10 images. Well, it doesn't look like it. But the more images I use, 40, 50, this is like a mystery movie, right? No. 100, 150! With 150 images, does it begin to look like the original? Say yes! Compared with the previous one. By the way, if I use a dictionary that has as many elements as the number of pixels in the frame, the reconstruction will be mathematically perfect. So long as the dictionary has some very simple characteristics. Another thing is, instead of using the dictionary that I showed you before, something like this with lines, we can use different kinds of dictionaries. I can use one with curves. I can use a dictionary of Chinese characters. I can use images from another film. And in each case, the reconstruction will be different. Here is an image from the Berlin Olympics, reconstructed with lines, curves, and Chinese characters. The same number of elements, each one has a different kind of feel to it. Here's two different dictionaries, lines and Chinese characters. These are mainly numbers. Can you see? Some you can still be seen. Okay. I have a video, I won't show it. Those, maybe during the Q&A you can ask me to play. This was from my exhibition. And this is what the work looked like in the exhibition. Okay, so here's explaining data compression. I will skip that, but I hope you understand it. If I give you a fixed dictionary, then any image can be represented by a set of numbers. Let's say you have 100, 200 elements in your dictionary. Each number tells you how to combine the different elements in the dictionary. So I have made a lot of works on this topic, and I was going to talk about them, but I think I will skip them because it's almost time. But basically, well, maybe I should introduce the latest one, just very briefly. Here, I'm doing the same idea. I'm taking a film, and I'm representing that film using a set of frames taken from that film. So here is Alphaville by Goddard, and I use an algorithm called simplex volume maximization to pick a selection of frames from the film. Actually 4 selections, 1, 2, 3, and 4. And then I try to reconstruct every frame in the movie by mixing these in the right proportions. Maybe I show you a little bit of a clip because this will be important as we talk about the new G. I'm skipping along. So here I'm using less than in the G. So these frames were selected by the AI as good representatives of the movie. So you can see that the computer is trying to make some of the frames brighter and darker to try to approximate the film. You might say, well, it's not a very good approximation, but it's because we are only using 1, 2, 3, 4, 3 times 1, 2, 3, 4, 5, 15 images. So with 15 images, we cannot do very much. But you can see that when the light goes on, these images become brighter. When it goes off, they become darker. Mm. So this is an approximation using 4 different dictionaries. And the computer will just multiply each image in the dictionary by a number, add them all together to try to reconstruct the origin. Okay, let's have like this. Okay. We're Heidi, coming almost there. Okay. Now, this idea of a dictionary is an essential idea in machine learning nowadays. Many machine learning applications use this idea. But one thing that some computer programs do, which I find very powerful and interesting, is this. If you give the computer a database of images, the computer will actually not use a fixed dictionary, but will try to create a dictionary based on this database. So let's say here's a database of faces. There is a method called non-negative matrix factorization. Sounds maybe a little bit scary, but the idea is quite beautiful. Because if you give the computer a set of images, it will find a dictionary. This is a dictionary where these are elements that can then be combined to try to reproduce each of these images. These are some images in the dictionary. They look scary. So here's the idea. If once you have a dictionary, then you might have some image in the database. Actually, it doesn't have to be in the database. It can be another image. And the computer will automatically give to every element in the dictionary a weight and then add them all together to reconstruct the original image. So this one, it will give a weight of 2.24, 2.03. This one, less weight. This one, even less weight. And then add them together to produce a reconstruction of the original. This method, in a way, is more interesting than the method I was using because it creates a dictionary, and the dictionary is quite special. It looks like every element in the dictionary is like a part of the face, right? Some looks like the forehead, some like the eyes. So this method is able to find parts in the data. Again, same idea. Here we are shifting the color from black-white to white-black. Never mind. This is a dictionary that the computer found from a database of faces. You can see some represent different parts of the face. And then, once you give it a face, the computer is able to mix them in order to reconstruct the faces. Math? Okay. All right. Now, here comes to the end. I'm taking this idea and using it to analyze movement in films. Let's go back to optical flow. Remember optical flow? I mentioned it a long time ago when you were young and innocent. So optical flow means that we take 2 frames in a movie and we give a representation of the movement in those 2 frames, right? Actually, we can use the method that I mentioned, non-negative matrix factorization, not just to decompose pixels, but to decompose motion. So we can take a lot of movement, not just one, a lot of movement as an input, and the computer will produce a dictionary of different parts of movement. Different parts of the movement. So it creates a dictionary that breaks down. Let's say you give the computer a lot of frames with a lot of the movement representation, a lot of optical flow frames. The computer will look at that and come up with its own dictionary. And I find that really interesting. Let me explain why. Now, let me put on my hat as a cinema studies scholar. When I went to school and to do my PhD in cinema studies, one of the lessons that we all had to go through was how to describe camera movement. How do we describe camera movement in school? How many of you here are film scholars? No, yeah, not a single person. Okay. Very often what we learn to say is this movement is a pan, tracking shot, zoom, right? We describe movement by describing what the camera is doing. Tracking means the camera is on tracks on the floor like a train and is moving. Pan means the camera is standing still but just pivoting, right? Zoom means the camera is standing still but the focal distance is changing. We don't have a vocabulary to describe the visual quality of movement in film. It's a bit like sound. Imagine that I say to you, I ask you, what is the sound that you heard? And you go, oh, the sound of a door closing. Don't tell me what made the sound. Describe the sound. It's hard to find this vocabulary. There was a French artist called Pierre Schaeffer who tried to develop a vocabulary to describe pure sounds. So I thought, what if I give the computer a movie sequence and I ask the computer to take that sequence, many frames, read the optical flow, find the arrows, and then break down that optical flow into many parts. And then this is like the language that we can use to talk about the movement in that scene. So for example, and I will show you some video clips and this will be the end. Here is a very complicated movement. It's a zoom. The camera is zooming forward. But it's not just a zoom. You see, there's a character, a woman, who is playing the drums. So you have the movement of the camera zooming forward. You have the movement of one hand, the other hand, the sleeves. She's wearing a Chinese costume, so the sleeves are also moving. Complicated movement. It's very hard to describe. But I use this method of non-negative factorization to take all of this information and break it down into different motion parts, creating a dictionary for each sequence. And yes, we should watch this. I better loop it. It's down here, right? This is loop. Is it loop? Let me show you. I'll show it to you a couple of times. Okay. So this is the original scene with the zoom. And the computer, I don't tell the computer what to do. Well, yeah, we write the program, but I don't say to the computer, please find the zoom, please find this, please find that. The computer uses math techniques actually based on the idea of optimization to decompose this movement into different movements. Can you see this one looks like a zoom? Right, like a thumb. This one too. some other movements, some other parts are responding to the hand. If you look carefully here, this section is responding to the shape of the drum, because as the camera moves forward, the shape of the drum has its own motion. This is a drum. Let me start it again. Sorry, I won't full screen it. Do you see that this is the shape of the drum? So this is responding to the hand drumming. Sorry, I'm playing it over and over again, but it's a bit difficult to follow it. Show you a couple more clips. This one is very beautiful. Sorry. Yeah, it's not so beautiful now. Let me pause it. Let me see. I think it's much better if we see the full screen. These are all films from the great director, Chinese director King Hu. And here we can see how it's responding. This is a beautiful moment because you have this character who is crawling, but the camera is also moving. Let me pause it because it's kind of crazy. And this is a very simple, very fast sequence. The same character moving from one room to the other. And you can see there are some horizontal movements which come up in different parts. This is a very simple one. So, by the way, I don't tell the computer how many elements to decompose the movie into. This one only does 1, 2, 3, 4, 5. I think it's only 5. But you can see some parts responding more to the waves, some parts responding more to the zooming forward. See, the top part is responding to the waves. This one is not really separating them into two parts. But here there's maybe more of the camera movement. There's more of the man over there. Yeah, so some. But for this one, the computer only finds two parts, which means the computer thinks the movement in this scene is less complicated than in the other scenes. For some reason in this one the computer found more. But notice, not as many as in the zoom. In the zoom shot in the beginning with the drums, it filled in the whole screen with so many different parts. The computer thinks this sequence is much simpler, so there are less elements. the last clip, which I think is quite nice. Let me go back. Here, this movement again is quite complicated because of all the trees. So the computer is finding different parts, but this one represents the overall direction of the movement. This part represents different parts of the movement because of the trees, and you have some in the foreground, some in the background. Okay, thank you. You can turn on the lights. And so, yeah, what did I do? Cancel. All right, so this is the work I'm working on now, and the visualization is using some idea from fluid dynamics. I won't describe it. It's called streak lines. But if you like the lines that I'm using in the visualization, they are coming from this idea from the study of fluid dynamics, which is the study in physics of flow. They study the flow of fluids like wind or liquids, but this can be applied to the flow of movement in a film. So I'm using something called streak lines. You can look it up afterwards. These are some still images from this visualization. All of this, the breakdown, deciding how many parts, is all done by the machine learning algorithm. Summary? And okay, some of you. And thank you very much. And if you're interested in the work, here's my website. So thank you very much. Comments, complaints, expressions of anger or disgust, or friendliness. Anyway, yeah.
When you compare the optical flow factor, and there's a slide showing the polar coordinate. And
not really polar coordinate, okay. Anyway, yes.
So you will compare two factors with the width of this coordinate.
Right. Yeah.
And but why don't you just do the factor subtraction instead of subtraction? What is it? Is the result different if you do that?
Yeah, go to the website. We have a diagram.
Yeah. Thank you. And by the way, let me say thank you. Just I mentioned his name, and he will be doing that talk tomorrow. Here's Sam Chan, who's my research assistant and my right hand and my half brain. Thank you, Sam, so much, because really I could not do the work without his support. Thank you, Sam. You are amazing and great, and I don't know what to say. So, okay. He's also very embarrassed when I give him.
I have a question.
Let me. Sorry. Let me.
No, the one back.
No. Just do it from here. Okay. No. This is not the one.
Yes,
The other one. Sorry. I have two versions of the work, and in the other version I use methodology. I think it's here. Okay. Now, it's very interesting. When we compare two things, what we do is we find the distance between them, right? How similar or different they are. And in math, there are many methods to compare things. Now, imagine that we want to. The typical method is what we call the Euclidean distance, which is, when we do geometry and we find the distance between 2 points on the plane, right? We often use Cartesian coordinates. We compute something called the Euclidean distance. Now, so for example, you have 2 points, right? The Euclidean distance is the typical distance between those 2 points that we could measure, okay? Let's say. Imagine that you are now going to compare vector A, this pair of vectors A and B, okay? If you look at the Euclidean distance between this and this, okay, it's just the length of the line joining them, right? Now, imagine, okay, you get the length, whatever this is. Now you have these two vectors, and imagine the length of the line joining them. Which one is going to be bigger, longer? This one, right? the line between them, which is the difference, so to speak, will be longer. But which two vectors are more similar? Intuitively speaking. Right? These two seem to be much more similar. These are perpendicular. So if you use the normal Euclidean measure, you will get these are quite different, these are quite similar. That doesn't work. Instead, this is explained in the website. In this, if we use this method, let's say one vector is here, one vector is here, they will be 2 steps away. If one vector is here and one vector is here, they're only 1 step away. So these two will be closer together. That was the reason. Make sense? The whole concept of finding the right way to measure distance is critical when you're analyzing images, when you're doing machine learning, AI, stuff like that. Finding the right way. Good question. Make sense? Yes. There is some research, if you like, in the website at the bottom. I believe that there is some, yes, which explains more clearly. It's 2 Korean scholars wrote an essay, Efficient Algorithms for Motion-Based Video Retrieval. And it's just go to my website. It's in the Gestus Redux project. Good, thank you. Yes,
I would like
sorry.
to ask, when you analyze the movie, but the movie maker, maybe they don't really have the
ideas that
yeah, but you just use this take the movie as the tool for you to develop something, right?
This is a complicated question, and I think there's no right or wrong answer. Some people would say that when you analyze a film, you should only discover what the filmmaker consciously intended. So, you would ask the filmmaker, did you try to do this, yes or no? Some people think that there is a lot in a movie that the filmmaker put there, but without thinking consciously about it. And there are many things that we do in everyday life of which we are not conscious, but we're still doing them, and they're still there. So, you're right. And then the question is, well, should we only find in the movie what the director planned to put them? And I think that we have a tendency, just my own opinion, okay? I don't want to dictate to anybody. You might say, hey, Hector, so what you're doing is doing something beautiful with those movies, is not analyzing them. Or you might say, Hector, what you're doing is nonsense. I think that too. But in my opinion, a lot of what is in a movie is not necessarily what people intend to put there, and that we often overemphasize planning. That we only want to find what the director planned to put there. But maybe human action is not just based on planning. That we do things without thinking a lot of times, and we can still find those things. For example, those movement patterns, I don't think the director really sat down and said, well, there will be 5 components in this movement. However, the director did plan how the characters would move, how the camera would move, created a music with those things. And I'm just expressing that in a mathematical way. Makes sense to you? Thank you, good question. Yes?
How is the sound generated for the Carvalho?
Yes. Oh, thank you for asking. Let me see if it's here. Yeah. Okay, let me play a little bit so you can hear it. I turn off the sound, so therefore you cannot hear it. Now you can hear that there is the sound of fighting, right? The sound is from the original movie soundtrack, but we have to do something. Have you seen the movie, The Grandmaster? You hear the movie, the sound, this scene is in the beginning. There's a terrible soundtrack. I'm sorry, maybe don't tell Wonka why I said this. It's a kind of very mainstream commercial movie soundtrack. So, mixed with the soundtrack, sounds of fighting. And I found the sounds of fighting very beautiful. But notice, by the way, now the sound stopped. I will explain why. So I found the sounds of fighting very beautiful, but the music really, really annoying. So we had to use AI, we had to use machine learning. Basically the same method that we use to break down movement into parts, we used to break down sound into parts. So in this method actually, with some manual labor too, thank you to Sam for that, managed to separate the sound of music from the real sound effects. So we removed the music and just kept the sound effects. That's why, let me play it a little bit again. There were some moments where the sound dies. That's because in the original movie, it was mainly music. So there was nothing else. If you remove the music, everything is gone. So if you hear it again, you will hear that the sound dies at some point. Just music. So you take away the music, nothing happens. Making this project, thank you, you can turn on the lights. Making this project was a lot of work, I can tell you this. Just doing this. Thank you. Does it make sense to you? So yes, the method is called non-negative matrix factorization. By the way, Minchi, I know you're working on image segmentation, so you can use this for image segmentation too. It's just a more difficult method. That's right. Yes.
So, is there a chance that certain cinema movement may match certain kind of soundtrack more? So maybe you can use this technique to try to find out the most relevant soundtrack or the best soundtrack for this cinema movement.
I haven't, but it's interesting. This is a topic that many artists are interested in. People like Kandinsky, and a number of artists are interested in finding correlations between the rhythm of music and the rhythm of images. Have you heard of a Russian film director called Eisenstein? He made a film called Alexander Nevsky, where there was a soundtrack by a famous composer called, I was going to say Pudovkin. What's the composer's name? Famous composer. Anyway, no? Prokofiev. So Prokofiev. Not that famous, maybe. And there was one scene in that film. I really recommend the film. One scene that is a battle on ice. And Eisenstein designed the scene very carefully so as to match the image with the soundtrack, and he found similar patterns of movement in the sound and the image, and he tried to match them. Not successfully, but it was an amazing project, and I really recommend you to study it and look at it if you're interested in the relationship between image and sound. So the film, and he did a diagram. You can find the diagrams online and in his book. The film is called Alexander Nevsky, and the filmmaker is Sergei Eisenstein. One of the landmarks in film. Again, it's not a successful experiment, but it's a beautiful idea. Thank you for that. Any more? I crammed a lot of material. I hope you're not kind of dying and I couldn't even finish, but I hope that it was interesting. Alright, thank you very much. Tomorrow, repeating Cantonese, and we have other talks. By the way, well, you missed it, I shouldn't say this. We had a talk last week by a biologist who actually had seen my work, and he was kind enough to mention my work. He said a lot of the ideas I use in my work are biologically accurate, in the sense that the way we perceive movies and the way we perceive the world corresponds to the way that I analyze movies. And after he mentioned this, I should tell you this. After I mentioned this, I looked online and I found that the way that I decompose movement is the same way that, well, not humans, but monkeys, probably humans too, respond to movement. The way that when we're looking at movement, we can recognize whether we are moving or not by analyzing movement, by breaking it down. And it's quite similar to the way in which I analyze Chinese films. So it's biologically plausible. Anyway, we had a biologist last week, and we will have tomorrow a repeat of this talk in Cantonese at what time? 3 or 2. Come at 2, and if it's not, then oh, okay.
Is there any country-specific series in your book?
At the moment, no. At the moment, no. I mean, I'm very interested in this topic, and I wrote an article. I don't know how good the article is, but I'm interested in this question. Where I wrote a piece, it was published in English and then translated into Chinese, about Chinese aesthetics in the cinema of King Hu. And I am interested eventually in thinking about how Chinese aesthetics relates to film. So it's something I'm working on. But at the moment, I think maybe first I analyze the movement, and then I see whether Chinese filmmakers and Western filmmakers might have different movement patterns. I think it's a really interesting direction. I'm also, by the way, interested in one concept in Chinese aesthetics. I don't know if I'm pronouncing it correctly. The concept of propensity. The propensity of things, which was written, I'm sorry, by a Western. I apologize for not mentioning a Chinese source. Francois Julian mentioned the concept of propensity, which is it sure? What's the tone?
Sure.
Fourth tone? Okay. Anyway, in Chinese aesthetics. And that concept inspired me to make work that would not just be about recognizing objects, but focusing not just on the form of the object, but on the movement that animates the form. So it was a little small inspiration only, but I think it was important that I was reading this book while making it. Still is a direction. Any more? So yes, we will have more events on this. We have quite a lot of talks, and maybe Winsome Wong, who is managing this event, will tell you a little bit about it.
Thank you, Hector. And also tomorrow we'll have Sam Chan at 3 o'clock in Cantonese version. So if you want to revise, then you can do tomorrow. And also at 4 o'clock there will be another talk about science fiction and books. And afterwards, in January, there will be mathematics and art and other talks as well. So when you leave, please feel free to get a leaflet about our upcoming talks and lectures. And also, please do come to our show starting from 27th of December.
In City Hall.
Yeah, in City Hall as like a part of our activity for celebrating School of Creative Media's 20th anniversary. Yeah. So, and also please do come to see Hector's work also, because I'm sure it's going to be good.
Well, I don't know, but
I've seen it.
I do think those of you who are artists, I would encourage everyone to consider bridging art and mathematics, bridging art and computer science. I am a mathematical idiot, and if I can do it, anybody can do it. And if you're a mathematician, think about working with artists. It's a huge inspiration for us. Okay.